First of all, I would also like to thank all the authors that contributed to this special issue. It was really a lot of work, a lot of interaction. Before I move forward to introducing the remaining papers, I would like to introduce a couple of concepts that are necessary to clarify the discussion. So Katsuhide just discussed weakly coupled multi-core fibers. Ideally, in these fibers, the cores are uncoupled with each other, and the signals transmitted in the individual cores can be received with independent conventional single mode receivers. However, if we want to increase spatial density, we have to squeeze the cores closer to each other. And if we do so, the signals start coupling during propagation. So in this case, we cannot receive them with independent receivers. We need a unified receiver, which means that we have to treat the spatial channels as spatial superchannels, and we need the multiple input, multiple output techniques to retrieve the transmitted signals. Of course, this implies an increase in complexity in the SDM receiver, but a major increase in complexity comes from the phenomenon of modal dispersion, which relates to the fact that different spatial modes propagate with different group velocities. And as a result, the duration of the impulse response of a fiber increases with propagation distance, of course, depending on the fiber type. Now, in the best case, it grows proportionally to square root of propagation distance. And in the worst case, it increases proportionally to propagation distance itself. In all cases, the duration of the intensity impulse of the fiber impulse response sets really the complexity of the MIMO SDM receiver. Okay, so this paper by Tetsuya Hayashi and the co-authors reviews coupled core multi-core fiber technology. Note that they refer to it as randomly coupled multi-core fiber technology because these fibers operate in a very special propagation regime where the coupling between the cores is actually random in nature. The paper explains very well that in order to achieve this propagation regime, the cores, the fiber cores cannot be too far from each other, they cannot be too close to each other, they must be just at the right distance so that coupling is dominated by random perturbations to the ideal fiber structure, which of course are always present in practice. The paper reviews the main design criteria of randomly coupled multi-core fibers, and they explain why this propagation regime is desirable. And this is essentially for two reasons. One reason is that this is the propagation regime in which modal dispersion accumulates proportionally to square root of propagation distance, thereby considerably suppressing the complexity of the MIMO SDM receiver. And the second reason is that these fibers have an enhanced tolerance to nonlinear distortions, a fact that has been understood theoretically and demonstrated experimentally in experiments that are also reviewed in the paper. The paper also covers characterization techniques of randomly coupled multi-core fibers, splicing technology, fan-in, fan-out technology, which is key to inject the signals in the fiber cores and to extract signals from the fiber cores, and cabling-related issues. It also reviews the first deployment of cabled multi-core fibers, which happened to take place in the city of L'Aquila in Italy. And it reviews some of the field trials that have been performed for both data transmission and fiber characterization. The paper by Pierre and co-authors reviews a few mode fiber technology. Few mode fibers are substantially different from multi-core fibers. First of all, they only have a single core of larger area, and they support propagation of multiple modes. They're characterized by the existence of multiple groups of modes, so that modes belonging to the same group couple strongly during propagation, just like in randomly coupled multi-core fibers, whereas modes belonging to different groups couple only weakly, of course, depending on how far they propagate. The paper reviews two regimes of operation. The first is called the weak coupling. The idea here is that the individual modes are received independently of each other, in which case it is very important to keep intergroup crosstalk as small as possible. And the goal of this approach is to maintain the MIMO SDM complexity low. The solution of choice in this case is a step index profile. And this is because step index fiber have mode groups with only either one or two spatial modes. The second regime of operation is called full MIMO. In this case, all the modes are received at the same time. And here it is imperative to keep modal dispersion as small as possible. And in this case, the solution of choice is a graded index profile. The paper reviews the main design criteria for these fibers. It also reviews the main transmission experiments performed in the two regimes of operation, as well as field trials and real-time implementations, and also the first deployment of cabled few mode fibers, which again happened to take place in the city of L'Aquila. The paper by Nick Fontaine and co-authors reviews components that enable SDM by interfacing single mode and the multi-mode technology. For instance, by allowing to multiplex and demultiplex single mode signals in SDM fibers. Now, this figure shows three types of photonic lanterns. The first two are made with tapering techniques. They connect a multi-core fiber and a multi-mode fiber, or single mode fiber bundle and a multi-mode fiber. These photonic lanterns can be mode selective, which means that it is possible to use a single mode signal to excite a specific spatial mode at the input of the multi-mode fibers. And these are examples of photonic lanterns addressing 3, 6, and 10 spatial modes. This is a different type of photonic lantern made with a different technique, ultra-fast laser inscription, which is based on the use of short pulse lasers that allow to inscribe arbitrary three-dimensional waveguides in a bulk glass cladding. And this type of photonic lanterns can be used, for instance, to make fan-in, fan-outs for single-mode multi-core fibers, demonstrated for more than 100 cores. The paper also reviews a multiplane light conversion technology, which allows to convert an array of spatially separated beams into a single beam to be coupled with a multi-mode fiber. This device allows to use the signal carried by any input beam to excite any spatial mode at the input of the multi-mode fiber, and is based on multiple reflections on a spatial light modulator. This is a picture of the device used to demonstrate a 45 mode transmission. The paper reviews the main design criteria of these devices, and provides a nice comparison between these technologies that I briefly introduced. The paper by Dan Marom and co-authors has been already introduced by Katsuhide. Once again, it is about optical switching in networks that make use of both spatial multiplexing and frequency multiplexing. The paper covers a wide range of network scenarios from undersea to data centers. And this is a very nice picture that illustrates switching options that are available in SDM networks, which of course depend on the regime of propagation of spatial modes. In particular, if spatial modes do not couple during propagation, as is the case in uncoupled core multi-core fibers, then frequency channels and spatial channels can be switched, can be routed independently. Of course, switching the entire spectral content of a spatial mode is an option of lower complexity. If the spatial modes couple during propagation, then the spatial modes, all the spatial modes at the same frequency must be routed together, must be switched together. They must be handled as a spatial superchannel to make sure that they travel together from the transmitter to the MIMO SDM receiver, all the way from the transmitter to the receiver. Of course, also in this case, it is possible to switch the entire fiber content altogether, which is, again, a solution of lower complexity. In general, the authors point out that pure spatial switching is an interesting solution for future networks where most likely most of the capacity comes from the spatial dimension, and therefore frequency selective switching may not be necessary. The last paper by Ed Zraip and co-authors covers a topic that is attracting more and more interest in these days, as it was clear at the last OFC. And this is using the global fiber optic network for environmental sensing. And the idea is that deployed fibers can be used not only for data transmission, but also as distributed sensors. The first approach to distributed fiber optic sensing reviewed in the paper is the more traditional one. It is based on measuring backscattered signals from Raleigh, Brillouin, and Raman scattering for the purpose of performing vibration, temperature, and strain sensing. The idea here is that each deployed fiber has a well-defined backscatter signature, so that perturbations can be studied by looking at the time changes of this signature. So this is quite a mature approach, quite a mature technique, but recently it enjoyed a considerable boost thanks to the availability of coherent receiver technology from the telecom industry. So the paper reviews all kinds of applications of these techniques, the theory and the main implementation schemes that are used today. The second approach to vibration sensing, which is reviewed in the paper, according to the authors, was stimulated by the observation that the optical phase measured in a deployed cable during an earthquake produced time traces that were strongly correlated with the time traces produced by a seismometer measuring the same earthquake. So the idea here is that vibration sensing can be performed not only by using signals dedicated to sensing, but also just by looking at data carrying signals received by a coherent receiver. So in this context, the paper reviews two field trials, one showing that various events could be measured by looking at the phase of data carrying signals transmitted in a terrestrial link. And the second, showing that it was possible to observe an earthquake by looking at the evolution of the state of polarization of data carrying signal transmitted in a transoceanic link. And altogether, this is just an amazing result. So with this, I conclude the presentation of these papers, and I'll give the word, I'll leave the mic to Vaishali.